Welcome dear friends. Today we are going to start with BCH code, which is a generic representation of cyclic code. In this chapter we are going to study binary BCH as well as non-binary BCH and one more code that is called as Reed-Solomon code or RS code. RS code is also a non-binary code. These all are extensions of cyclic code. So cyclic code is the main code. So we have seen coding techniques. So under that we are having a linear code. Under linear code we are having linear block code and cyclic code. Under cyclic code now we will be having BCH code and RS codes. So here we are going to understand all the concepts that how exactly from a given value of n we can calculate the generator polynomial for different error correction capabilities. From that how we can understand the generator polynomial, and then for given value of n and given value of error correction capability how can we calculate the order of the code. For encoding and decoding, the process that we studied for cyclic code is going to remain same. So encoding will be exactly same, but there will be a change in the decoding process. So decoding of BCH is completely different, but the hardware implementation remains same. So BCH code is, just understand that it's a generalized cyclic code, or we are going to understand a complete method of finding out the generator polynomial, order, error correction capability, everything for BCH. There is some prerequisite mathematics which is known as discrete maths, which we haven't studied in our course of engineering. So here all the prerequisite whatever required that we will be studying for first few slides, and then in the next set of slides we will be starting with BCH code. Here the first concept that we are introducing is a finite field. So what is exactly finite field? In the mathematics we have studied set or number set. So we start from natural numbers, whole number, real number, and so on. Here the first concept is a field. What is a field? Field is a set of numbers or set of elements. These set of elements are so special that if you perform two basic operations, that is addition and multiplication, the result is available in the set, and then we set the field or as a closed field. So here what exactly it tells, let's understand through one example. If I consider a single digit number, my single digit numbers are from 0 to 9. So it's the set of elements. So this is a field. But this field is not closed under addition and multiplication. Now why I'm saying that it's not closed, the reason is if I perform 7 plus 5, the result will be 12, and my single digit numbers are from 0 to 9. So 12 is not the part of the set, hence that field is not a closed field. I hope this example clears your idea about closed field. So this is an open field, but here we are going to have a concept that is field, and field is always closed. So when I say a result as closed, as we discussed, 7 plus 5 becomes 12. But instead of that, if 7 plus 5 becomes some number which is from 0 to 9 again, then I can say that the field is closed. Now the question comes, this is not in our routine or day-to-day mathematics. So yes, it's not there in our day-to-day mathematics, it's slightly different from that, and that is what we are going to study now. So what it says right now is, let's say that I am having a field which is normally called as GF. So here it is GFQ is written. So what is GFQ? GF is Galois field. A person who has developed this concept is a Galois, and the field is there of Q. So Q is the number of elements. So GFQ means it's a field of Q elements. So it has got certain conditions on it which are written over here. The first condition is the operation is close. That is, if I have got two elements alpha and beta, as you can see in the first point, the alpha and beta are the elements of set F. So alpha belongs to F, beta also belongs to F. That is, alpha and beta are the two elements that belong to set F. So if I perform alpha plus beta and that result also belongs to F, and alpha into beta, that results also belongs to F, then I say that the field is closed or the operation is closed. So I hope this clarifies your simple concept that what is close in. So close is simple answer for close is when I perform certain operation, the result is also available in the set, then it is the closed field. For a field to be complete, there exist two elements, unique elements, that is 0 and 1. So that is your point number 2. So there exists a unique element in F which are denoted by a 0 and 1, such that if you add 0 with any element of the set, the element remains same. So that's why 0 is called as additive identity. And when you multiply 1 with any element of the set, the element remains same. So that is what is written. Alpha plus 0 is equal to alpha. So that is additive identity. Alpha into 1 is equal to alpha, that is multiplicative identity. So 0 is called additive identity, 1 is called multiplicative identity, which is just the normal concept of our mathematics. Now for every element alpha, there exists another element beta in such a way that alpha plus beta is equal to 0. So when the two elements added together makes the result 0, we call them as additive inverse. So here alpha and beta are additive inverse of each other. So for every element alpha, there must be some element beta which is additive inverse of it, and it's a part of field. So this is one more requirement of the field. So what we have seen in this slide is what is a field and how the elements of the field are related with each other. So we are restricting ourselves only for two operations, addition and multiplication. We don't have subtraction and division for a field. So please remember this. Now let's continue with the field concept again. So in the last slide we have seen what is a field, how the elements of the field are related. So we are talking about some inverse elements. So in the last slide we have seen additive inverse. So when two numbers are added together and result becomes 0, so then we say that the two elements are inverse of each other. In the same manner, if two numbers are multiplied with each other and if the result is 1, then we say that the two numbers are multiplicative inverse of each other. This concept we will be using extensively specifically for decoding. Please remember. So the first point of this slide is, for any non-zero element alpha, there exists a unique element gamma such that alpha into gamma is equal to 1. Then we say that alpha and gamma are multiplicative inverse of each other. So the fifth point is, all the rules which are satisfied in our normal mathematics, that is commutative, distributive and associative, are applicable for field also. That alpha plus beta plus gamma is equal to alpha plus beta plus gamma. So the meaning is, you add them in any order, you give priority to any numbers for addition, the result is going to remain same. So this is what we called as associative property. Second is, alpha plus beta is same as beta plus alpha, which is commutative property. That is for addition we have seen associative and commutative. Same is there for multiplication. Alpha into beta multiplied by gamma is same as alpha into first beta into gamma. So the meaning is, again multiplication satisfies associative property alpha into beta is same as beta into alpha, which is commutative property, and the last one is a distributive property. So the field which has got finite elements is known as finite field. The best example of finite field is a binary field that we will see in the next. So the number of elements in the field is called as order of the field. So this is the first definition to remember. Now we are thinking about field because there will be another term, order of the element. So don't confuse with these two. Right now we are thinking about field, not about element. So the number of elements in the field is called order of the field. So binary field has got two elements. So which two elements it has got? 0 and 1. So order of this field is 2. Now if you recall, binary field satisfies all the properties. Why it is called as field? Because all the operations of addition and multiplication are close. For example, 0 plus 0, 0. 0 plus 1, 1. And 1 plus 1, 0. So all the results are available in the field 0 and 1. Similarly about multiplication, 0 into 0 is 0, 0 into 1 is also 0, and 1 into 1 is 1. So again results are 0 and 1 which are available in the field. So here the addition we called as XORing and multiplication we called as ANDing. So binary field satisfies all the properties of the field. So 0 and 1 are two elements. 0 is additive inverse, 1 is a multiplicative inverse. So 0 has got additive inverse 0, 1 has got additive inverse 1, right? Because 1 plus 1 is 0. So 1 itself is the inverse of itself, right? So all the properties of field that we have seen in last two slides are satisfied by 0 and 1. That's why the basic and the simplified field is a binary field that we are aware of. Now we are going to extend this concept in the next slide. Right now we are having binary field where the order is 2, that means it has got two elements. If I may have more elements, how the field will look like? So let's go for next example in the next. Now the next example that we consider here is a prime field which has got 7 elements. So the elements are 0 to 6. Now these elements are given to you or shown to you along with the two tables. The first table is a addition table and the next table is the multiplication table. Here to perform the addition and multiplication we are going to use the rule that is mod 7. So what is the meaning of mod 7? If the result, whatever result I will get, I will divide it by 7 and the remainder will be my final answer. So it's not the addition or subtraction. Whatever result of addition and subtraction will be there, I am going to divide it by 7 and the remainder will be the final answer. For example, here you can see 3 plus 5, sorry 3 plus 2, result will be 5. So 3 plus 2 will be 5. You can cross check in the table. Okay, take 3 from column and 2 from row, addition will be 5 or vice versa. But if you perform 3 plus 6, what will be 3 plus 6? In our normal mathematics, 3 plus 6 will be 9. So divide this 9 by 7. So when you divide 9 by 7, remainder will be what? So I will have quotient 1 when 9 will be divided by 7. Quotient will be 1 and remainder will be 2. So my addition result will be 2. So you can cross check. 3 plus 6 will result into 2. I hope you understand this. Similarly, take 2 plus 5. 2 plus 5. What will be the result? 2 plus 5. Addition will be 7. Divided by 7 again. As the number exceeds 7 or equal to 7, divided by 7. 7 divided by 7. Quotient will be 1. Remainder will be 0. So what is the answer? Remainder. And what is remainder here? 0. So you can cross check. 2 plus 5. So you can take 2 from the row and 5 from the column. Answer will be 0. So whenever two elements will have addition 7, like 3 plus 4 or 6 plus 1, the result will become 0. And that's why these elements are additive inverse of each other. That means 5 plus 2 are additive inverse of each other. 3 plus 6 additive inverse of each other. 6 plus 1 or 6 and 1 are additive inverse of each other. So here you can see that the result of this addition process is bounded between 0 to 6 because I require 7 elements. So my 7 elements are always from 0 to whatever the element minus 1. Like binary field, it has got 2 elements. So what the 2 elements are? 0 and 1. So it's not 2. Similarly, this is GF7. So 7 elements are there, but 7 is not a part of the field. So field will be from 0 to 6. So that we have seen in any of the digital systems process, or when you say 4-bit number, 4-bit numbers are not 6. Actually 2 raised to 4 are 16, but the number of elements are 16 are there, but they starts from 0 to 15. Now start with the multiplication. So multiplication, again the same rule we are going to follow. 0 into any element will become 0. That's why first row and first column will be is 0 of this result. 1 into any element is going to remain same. Now if I have 4 into 2 or 3 into 2 first, so 3 into 2 will be what? 6. 6 is less than 7, so if I divide it by 7, my quotient will be 0 and remainder will be 6. So there is no problem in the result. 3 into 2 will become 6. But if I take 3 into 4, what will be the result? 3 into 4, normal multiplication is 12. 12 mod 7 or 12 divided by 7, and remainder is what? So 12 divided by 7, quotient will be 1, the remainder will be 5. So that's why 12 mod 7 will become 5. So 3 into 4 results to 5. Got this? Similarly, 4 into 2. What is 4 into 2 will be? 4 into 2 will be 8. 8 mod 7 will become 1. Right? So 8 mod 7 is 1. So the multiplication of 2 and 4 comes to be 1. So when the multiplication of two numbers is 1, those are called as multiplicative inverse. That's why 4 and 2 are multiplicative inverse of each other. Similarly, 3 into 5. So 5 3s are 15. 15 mod 7 will become 1. So 3 and 5 are multiplicative inverse of each other. And 6 into 6, 36. 36 mod 7, remainder will be 1. So 6, it's multiplicative inverse of itself. So I hope this slide will clear your all concepts of closed field. So requesting you all to first go through first 3 or 2 to 3 slides where all the concepts of field are given and apply in this slide so that your concept of field will become clear. Now once you understand the field concept for numbers, then we can extend it to polynomials. Right now we kept it much easier. Right now we are only restricting ourselves to numbers. In the next slides we will be extending it to polynomials. I hope what I taught you right now for first 5 slides everyone understand this. Requesting you all to go through the 5 slides again, revise the things, apply on your own. I'm pretty sure you will understand all these concepts. Okay? So thank you here for completing field for numbers. Now here we are using a prime number, that's why it is called as prime field. Okay? So let's finish with field and let's go to the next slide. Now once we understand what is exactly field is and what all properties it is supposed to satisfy, let's consider a field which has got order as a prime number, and that field is called as prime field. This prime field is the most useful field and that's why it is specifically considered. So how it is defined? For any prime number p, there exists a finite field of p elements denoted by gf of p. As p is any number, the elements will be always finite. The example that we have seen in last slide, gf7, where 7 is a prime number and it has got 7 elements, or order of the field is 7. hence that field is considered to be a prime field. So if it is GFP, it will have P elements and therefore order of the field is P. Another field that we have seen in the beginning is a binary field, and binary field has got two elements, so its order will be 2, and where 2 is again a prime number which has got two elements 0 and 1, that is also a prime field and the most simplified field. But if it happens that I am supposed to extend the field or I am supposed to increase the elements of field to any number, but that number is not prime, then is it possible to construct a field? So the answer is yes. For example, if I want the field of 16 elements, is it possible? Yes, it's possible, because 16 can be written as 2 raised to 4. So I'm going to take fourth power of binary field. That means it is called as fourth extension of the field. So in a generic manner, I can say that for any positive integer m, it is possible to extend the prime field GFP to the field of p raised to m elements, which is called as extension of GFP, and it is denoted by GFP raised to m. So the basic field is GFP, and GF of p raised to m represents its mth extension. Now why we do this? The answer is quite obvious, that I am supposed to increase the elements of the field, but it may possible that the field may not be prime in that case, and when I am going to consider the field which has got order which is not a prime number, but still it is supposed to satisfy all the properties of prime field or of a Galois field or closed field, then I have to find out extension of the basic field. So this is called as field extension, and always remember, field extension will satisfy all the properties that we have studied previously without keeping the order as a prime number. Okay, so this prime field will be most important for us, because this is what exactly we are going to do when we will be solving BCH or RS code examples. This will be our first or second step to extend the field. So that's why we are studying it right now. So here we have got extension of the field. Now in this slide, we are going to consider one of the important concept which we will be using while solving the example, that is primitive element, and how this primitive element is useful to design a complete field. That theory or basics we are going to understand. So let's start. So we consider a field to be cyclic if there exists a element whose power will construct a complete field. That means by taking different power of this element, if I can construct a complete field itself, okay, then that element is important for us. Now here, to understand this concept correctly, let's take the example of GF7, which we have seen 2 slides back. So GF6 or GF7 has got elements 0 to 6. Out of that, 2 elements are default elements, 0 and 1. So what remains is the elements from 2, 3, 4, 5 and 6. So these 5 elements I am supposed to get from a single element. So here we consider a special element 3, and the special element is going to give me all the elements. Now how it is going to give me? I will take a different powers of 3 and divide it by 7 to calculate the remainder. So what I do is 3 raised to I mod 7. This is what the calculation I am going to take. So take different values of I. Let's say I is equal to 0. So it will be 3 raised to 0. 3 raised to 0 will be 1. 1 mod 7 will become 1 again. 3 raised to 2 or 3 raised to 1 will be 3. 3 mod 7. So 3 is less than 7, remainder will be 3 itself. Next will be 3 square mod 7. So 3 square is 9. 9 mod 7. So remainder will be 2. Next will be 3 raised to 3 mod 7. 3 raised to 3 will be 27. 27 mod 7 will become 6. Then 3 raised to 4 mod 7. 3 raised to 4 is 81. 81 mod 7 will become 4. 3 raised to 5 mod 7. 3 raised to 5 is 243. Mod 7 will become 5. You can calculate all these on your own. 3 raised to 6. 3 raised to 6 is 729 mod 7. Answer will be equal to 1. Now we have 3 raised to 0 is 1 and 3 raised to 6 also has 1. Now if I go one more element higher, so it will be 3 raised to 7. 3 raised to 7 will become, I think it's 2187. 2187 mod 7, answer will be equal to 3. So I am getting the elements back, or it's repeating. So initially I have got a 1, then 3, then 2, then 6, 4, 5. Again it's same, 1, 3 and so on. So that means by taking different power of 3, I can construct all the elements of the field, and after certain limit that is repeating, that's why it is called as cyclic. So what we understand right now is a field which is a prime field, in that I always have one element. By taking the different power of that element, I can construct the complete field. This is the first point that you should remember. So how we are going to utilize that? So for any non-zero field element alpha, so there is one element we are considering alpha, there must be a positive integer n such that alpha raised to n will become 1. Then this value of n is called as order of field element alpha. So in the previous slides I told you, do not get confused with the order of field element and order of the field. So here is a time to recall that. Order of the field is number of elements in the field, and this is the order of the field element. So when you say the field element as order is n, when alpha raised to n is 1, that means when it's becoming cyclic kind of process, then you call the order as the, or that number as the order of the element. So for the previous example, we have seen that 3 raised to 6 becomes 1. So in the previous example, 6 was order of the element 3. So order of element 3 in the GF7 is 6. Okay. Hope this clarifies the concept, and try to understand the wordings very clearly. So order of field element alpha is n if alpha raised to n is equal to 1. So in the previous example, 3 raised to 6 is equal to 1. So 3 was my alpha and n is 6. That's why order of 3 is 6 in the previous example. Hope this clarifies this point, order of field element. So we have got a special element. That special element has got the order, and by taking different power of this element, I can get all the field elements. To have a cyclic, we require order. Now this element has given a special name, and the name of the element is primitive element. So when we say a element as the primitive, so let's understand this concept. A field GF cube, or in a field GF cube, a non-zero element alpha is said to be primitive if order of alpha is q minus 1. So q is the number of elements in the field, minus 1 if this number, so q minus 1 if this number is the order of the field element alpha. Yeah, so q minus 1 is the order of field element alpha, then that number alpha is called as a primitive element. For example, in the previous example, there can be some other elements also. By making or by taking their powers, you can construct the complete field, but I will choose a element which is primitive. So you can do this exercise, that you can take different powers of other elements also. You can take power of 2, 4, 5, and you will get that by using higher orders and taking mod operation. You can construct the field, but all of them will not satisfy this condition. That order of the element is q minus 1. For example, in the previous case, 3 raised to 6 mod 7 becomes 1, where q is 7, number of elements in the field was 7, so q minus 1 is 6, and 6 is the order of element 3. That's why 3 is considered as the primitive element of GF7. So this primitive element is really important to design a complete field, and every time we will be treating alpha as a primitive element, and by taking the power of this alpha we are going to construct a complete field or a closed field. Okay? So here we finish with this slide. The most important concept, primitive element and its order. This concept beyond finite field, that is extension of the field, we have already seen that if I have a GFQ field where q is a prime number, and if I want some another number which is the mth power of this prime number, then I can have GFQ raised to m, and that I can get by taking or the field that has a GFQ raised to m, and that also satisfies all the properties of prime field. So the best prime field that we are aware is a binary field, and these binary elements can be extended to get another field. For example, we use all the binary mathematics to perform the operation, but in a microprocessor we never use a single bit or single digit numbers. We use 8-bit microprocessor or 8-bit microcontrollers or 16-bit microcontrollers. So that from single bit to 8-bit what we are going, that is called as extension, so that we can have for the field. So if I have got a 4-bit field, then I can say that it is GF2 raised to 4. So I can write down this as GF2 raised to 4, so which will have 2 raised to 4 elements in it. So in the generalized manner, if I have GF2 raised to m field, then it has got 2 raised to m elements in it, which is the extension of binary field. So here what we have done by this time is we understand the concept of field, what are the rules of this field are, how to get the field, how to extend the field from a special element that we have seen. That element we called as primitive element. Now what all we have discussed is only on numbers. Now it's a time to shift from number to polynomials, because if you recall cyclic code works in the form of polynomials. Hence we are going for polynomial representation of the field. So let's understand few of the concepts of polynomial, and then how this will be used in the form of polynomial, that we will study in subsequent slides. Okay. Let's start with the concept polynomial representation with GF2. Now this is we have already seen, or we are familiar with this for the cyclic code. In the case of cyclic code, you might recall that a binary vector or a message vector or code vector which is having binary coefficients or binary values can be represented in the form of polynomial. For example, 1 1 0 0 can be represented as x cube plus x square. So what we have done in this case is the polynomial which is in the form of x has the coefficient from binary values, that is When the element is present, its coefficient is treated as 1. When the element is absent, its coefficient is treated as zeros. So a simple thing we are considering now, that a polynomial is there whose coefficients are from binary field GF2. So let a polynomial fx with one variable x and coefficient from GF2 is of the form fx is equal to f0 plus f1x plus f2x square plus f3x cube and so on up to f suffix n x raised to n, where this f values are either 0 or 1. Okay, and I goes from 0 to n. So degree of the polynomial is the largest degree of x. So the fx will have degree n provided that this fn value is also 1. If this fn is 1, then only x raised to n terms will be present. Otherwise this term will be absent or will not be there because it is multiplied by 0. So this is the polynomial with degree n, provided that a coefficient corresponding to that has got value 1. Now the rules of multiplication and addition of these polynomials are same as what we have seen in the case of cyclic. It means they follow some modulo operation, like 1 plus 1 becomes 0. So when same number is added, the result will become 0. So it will follow the same kind of operation, or modulo x raised to n multiplication, which we have seen for multiplication process, or even for some kind of polynomial operation we have seen that, right? So that will be followed. So here are certain rules. Again the rules are same: commutative, distributive and associative. So if two polynomials are there, ax and bx are there, so a of x plus b of x is same as b of x plus a of x. Same follows for multiplication also. A of x into b of x is b of x into a of x. Associative, the order of the elements in the addition or polynomial order of the polynomial order does not matters for the case of addition. The result is going to remain same. Same is about multiplication. So even though you interchange the order of these polynomials, the result will not be, or result will be same. It will not be affected. Distributive, so it's a combination of addition and multiplication. So if you have two polynomials, you add them and then multiply by some third polynomial, then that you can have individual polynomial multiplied by or by a polynomial, and then you perform the addition. So when fx is some polynomial that is divided by g of x, the remainder r of x is 0. So this is Euclid's division lemma that we are actually trying to understand. So when a polynomial is completely dividing another polynomial, then we say that the divisor polynomial is a factor of dividing polynomial, right? So g of x is a factor of f of x. So this is the simple concept of polynomial division that we are aware of. So for a real number a, if a is the root of the polynomial fx, then we say that f of a is also 0. This is the concept of zeros that we have studied in 9th and 10th. So zeros of a polynomial. So a number whose value, if you substitute in the polynomial and that polynomial itself becomes 0, then that number is the root of that polynomial, or 0 of that polynomial, and from that you can calculate the factor. That is, if x is equal to a is the root of the polynomial, then x minus a is the factor of this polynomial. But as here we are having modulo 2 operation, x minus a is also treated as x plus a, because for modulo operation addition and subtraction are treated same. That's why x minus a is same as x plus a. So this is about the polynomial division and root of the polynomial. So basic operations of polynomial you can say we have discussed here. Now let's start with some another concept related to polynomial and then relate them with field. the concept of irreducible polynomial, which is same as the concept of prime number. Okay, so we have seen prime field where the number of elements in the field are prime, GF7 if you recall. Similarly, what do you say? A prime number, a number which does not have any factors, that's a prime number. Same is the case with the polynomial. When a polynomial cannot be further factorized, is called as irreducible polynomial, or polynomial which does not have any factor is called as irreducible polynomial. So a polynomial px over gf2, now these wordings are also important. Over gf2, that means it is having coefficients from 0 and 1. So a polynomial px over gf2 of degree m is said to be irreducible over gf2 again. Okay, if p of x is not divisible by any polynomial of degree less than m but greater than 0. Then what we can say, if it is not divisible means it does not have factors. So that is what a simple concept. If p of x is not further divisible, then it is called as irreducible polynomial. So fx is a polynomial, or fx is from the set of polynomials kx. So if fx has no proper divisor in the set kx, that is among the 4 polynomials of degree 2. So we are considering an example of fx which has got degree 2. So how many such polynomials are there? 4. So x square plus x square plus 1 x square plus x and x square plus x plus 1. This is the set of 4 polynomials. So this is set is a kx. So out of that, 3 are there which are divisible either by x or by x plus 1. Now here how we say it is divisible by x or x plus 1. When you say x is there, so equate x with 0. So what we get? X is equal to 0. And when you equate x plus 1 is equal to 0, what I got? X is equal to minus 1. But here plus 1 and minus 1 are treated as same, therefore x is equal to 1. So I got 2 values of x because it's a binary polynomial. Either x is equal to 0 or x is equal to 1. So when the polynomial is x, that means it is x is equal to 0. And when the polynomial is x plus 1, that means x is equal to 1. These are the two roots. So x is equal to 0 and x is equal to 1 are the roots. And x is and x plus 1 are the polynomials for these roots. What we talk in the normal mathematics terms. So x square is divisible by x. That means if you substitute x is equal to 0, the x square value will also become 0. That's why 0 is the root of this polynomial. X square plus 1, if you substitute 0, it will be 0 square plus 1 will be 1. So 1 is non-zero number, so remainder is 1. So 0 is not the root of this polynomial, but if I substitute 1, 1 square will be 1, 1 plus 1 will be 0. So root of this polynomial is x is equal to 1. That means x plus 1 is the factor of this polynomial. Same way, x square plus x, if you substitute x is equal either 0 or either 1, then it will become 0. That means 0 as well as 1 both are the roots of this polynomial, and x plus 1 are the factors of this polynomial. But if you go for fx is equal to 1 plus x square, you substitute x is equal to 0. So 1 plus 0 plus 0, answer will be 1. And if you substitute 1 plus 1 plus 1, still answer will become 1 because it's a XORing operation. It's not normal operation. So it's modulo 2, that means XORing operation. So in both the cases, fx answer remains 1. So fx of 0 is 1 and f of 0 is 1 or f of 1 is also 1. So even though you substitute 0 or 1, it is not divisible. That's why it is irreducible, as either 0 or 1 is not the root of this polynomial. So this is not either divisible by x and this is not divisible by x plus 1. So x square plus x plus 1 is the second degree polynomial, second degree binary polynomial, which is the irreducible polynomial. So from the set of these 4 polynomials, only x square plus x plus 1 is the irreducible polynomial. Getting this? Similarly, if you have fx is equal to 1 plus x cube plus x square plus x cube, This has got factor 1 plus x and 1 plus x square. Now this has got two factors. So this is reducible or irreducible? So this is a reducible polynomial, right? So here we finish a point. Irreducible polynomial. A simple concept of irreducible polynomial is a polynomial which does not have a factors or which does not have a roots is called as a irreducible polynomial. Now let's start with the concept called as primitive polynomial. So primitive polynomial, this concept is extension of primitive elements. So if you recall few slides back, we have seen that there is a special element in the set of prime field. By taking the power of this field, we can construct the whole field, and the order of this element is q minus 1. Then that element is called as primitive element. Same is the case here, but it's slightly different as it is applied for polynomials. So if you have irreducible polynomial of degree m, then it is said to be primitive if it satisfies two conditions. First, the polynomial is an irreducible polynomial, and second, this polynomial should be the factor of only one polynomial, or should be the factor of polynomial of degree 1 plus x raised to m, where m is 2 raised to m minus 1. So if the primitive polynomial has got degree m, then it should be the factor of one polynomial. It should be the factor of the polynomial x raised to n plus 1, where n is 2 raised to m minus 1, but it should not be the factor of any other polynomial less than that. So here are the two conditions. An irreducible polynomial p of x of degree m is said to be primitive if the smallest positive integer m, for which p of x divides, is x raised to n plus 1, where n is 2 raised to m minus 1. So this is the smallest degree polynomial px. So fx is irreducible of degree n, which is greater than 1. So fx has got, or fx is irreducible polynomial. Second is fx is not a divisor of 1 plus x raised to m for any value n which is 2 raised to n minus, which is less than 2 raised to m minus 1. So these are the two conditions for primitive polynomial. Now if you see 1 plus x square is a irreducible polynomial that we have proved in last slide, and it's not a factor of any polynomial 1 plus x raised to n where n is less than 3, because m is 2, degree of this polynomial is 2, so n is what, 2 raised to m minus 1, so 2 raised to 2 minus 1 will be 3. So it's not a factor of any polynomial 1 plus x cube or less than 1 plus x cube. That's why it is primitive polynomial. Another example of polynomial which we have chosen is fx is equal to 1 plus x square plus x cube plus x raised to 4. So what is the degree of this polynomial? 4. So here m is equal to what? M is equal to 4. So in this case, as m is equal to 4, n will be what? 2 raised to m minus 1. So 2 raised to 4 minus 1 will be 15. So it should not be the factor of any polynomial which is having degree less than 15. But if you look here, it's a factor of 1 plus x raised to 5. So as it is a factor of 1 plus x raised to 5, that's why even though it is irreducible, this is not primitive polynomial. So these are the two conditions for primitive polynomial. Hope so you understand this primitive polynomial, and we are not supposed to bother about this primitive polynomial much, because as we have given the primitive polynomial set by the mathematicians, we will be just using this primitive polynomial of different degree, where degree of primitive polynomial will be treated as m. Here is the list of primitive polynomials for different values of m. So we have taken it from m is equal to 3 to m is equal to 24. You are not supposed to remember any of this polynomial. Okay, just for m is equal to 3 or m is equal to 4, if even though you remember these two, our job will serve, because for solving the examples of BCH and RS codes, we will be requiring these primitive polynomials, and every example will start from primitive polynomial. So for m is equal to 3, we have got primitive polynomial 1 plus x cube, and for m is equal to 4, we have got primitive polynomial 1 plus x raised to 4. Now how to use this primitive polynomial and all that you will understand in subsequent slides. So here we finish with the first part of basics of BCH code. Now with this foundation, we will be starting with constructing a Galois field, which is the extended Galois field by using these primitive polynomials, that we will be starting in the next lecture. So this is all for today's lecture. So good day for all of you. And I know these concepts are completely different, or these are completely new to us. So I will be requesting you to again and again listen this lecture and note down all these concepts. So next lecture will be again a basics, which is important, and next lecture we will be finish all the basics and we will reach up to the steps of BCH code, or steps to get the generator of BCH code. So the first half of BCH and RS code we will be finishing in next lecture.